Welcome to SOH, the best office hours ever, because you are part of it. 2024, question number 2, the one that we need calculator or Desmos to derive some of the results. So let's begin by reading the problem, making sure that everything is clear. You can try to solve it by yourself, that's great. Then come back with your 5 to see some details, or correct me, that would be even better. You have to get better at this than me, okay? So a particle moves along the x-axis so that its velocity for positive times is given by this. Well, first thing to notice, there are no units. So don't worry about them, but do worry about them if you read any units like meters, kilometers, minutes, whatever. Then your answer must always include the proper units or you will get some points off, and we don't want that, right? Especially those points are pretty expensive with how much exam it is, and also all the amount of time that we have put into it. So let's see. There is one time t equal tr in this interval, so that's something that we have to pay attention to, this interval, when the particle is at rest, so it's not moving. Okay, thank you, yes. So this basically means when the speed is 0, right? Okay, cool. So we will have to solve that with Desmos or a calculator and just get it. Okay. Then the next thing will be, if it's moving to the right or to the left, we will be using here the usual convention of mathematics that an x-axis pointing to the right is positive and negative to the left. So if the speed is positive in that interval, it's moving to the right. If it's negative, it's moving to the left. Now, B. Find the acceleration of the particle at t equal to 1.5. No units, you can see, no units. Show the setup. Okay, well, there are 2 ways to solve this problem. Now that we have Desmos or a scientific calculator, one, just use Desmos. You tell Desmos, look, this is my function, this is v, compute the derivative at 1.5, and it will do it for you. Okay, second way, compute it yourself, but that's optional. Okay, and then substitute the time and double check that the answer is the same. Of course, at the level of AP, calculus, you don't need it. You just call Desmos, because, hey Desmos, I'm hungry, breakfast please. And that's it, Desmos does everything for you. But, you know, in life sometimes you won't have Desmos to prepare breakfast for you. If you are in the middle of the forest, no? Then you will have to prepare it by yourself. So what do you do then? Well, then you compute the derivative by hand and substitute 1.5, have fun, do a hike, and enjoy the day. So sometimes doing things by yourself may be pretty important because you may be wondering about some approximation, some project that you're doing, some new idea. And when you do it by hand, you can see the simplifications that are happening and what would you do to do this or that or the other. So which part of the system or your idea you would put more attention into it. And that will give you an edge over other people that are Desmos-like, okay? So, but anyway, that's how it is. The position of the particle, at some time we have the speed, it's going to be an integral. That's also kind of a problem that you have a derivative and they ask you about the integral. So it's like, okay, the first question, there was a coffee with a temperature that was changing and also required to do something similar to this. So the final temperature was, here's the final position, was the initial temperature, here's the initial position, plus an integral that goes from the beginning to the end of your derivative. Your derivative here would be this, but of course, the notation for x prime, the derivative with respect to time, is usually the speed, right? So you will have that. Again, Desmos in this case, and that's fine. Notice that this speed doesn't have an absolute value around it, it's just the speed, because it could be positive and negative. The question is the position. So imagine that I'm here. Hey, I'm indeed here, I'm not anywhere else. And then I move 1 meter to the right, and then I move 1 meter to the left because I forgot my wallet. It happens all the time. So where is my final position? 0. Back at the beginning. Woo! Now, how much I've walked? 2 meters. So I spent 2 meters to get my wallet instead of just remembering and get it at the beginning. That's how it is. So it's different position than distance. Position might be 0 at the end, and distance is what it took. So when we derive the distance, this is the next question, you're going to do a similar thing, but your integral, and then you don't have to add the initial position because you are not computing position, you're computing distance. It's going to be the absolute value. It's always positive. You always have to do something. +1, and then +1 again, back. So, okay, and it's going to be this. So also with Desmos, you can do it. And there's another way, which is to break down this integral when VDT equals to 0 and break it down into intervals. When you have here positive, if it's negative, you put a minus, and if it's positive, a plus, okay? That's also nice to see, you know, how each interval contributes to the total distance. But you know, these days it's all about Desmos, and you are just Desmos users, so we will do it. Okay, this is it. This is it. Maybe you want to try to solve it. Otherwise, in the next questions, we will do it, and I will also show how to do it with Desmos, which is great. You know, Desmos is great. It's really helpful to do a lot of things. But the only thing is that, you know, it's kind of just too simple to solve these problems just with Desmos. Okay, so let's see. A particle, the first one is to find the zero of this function. Okay, so what we have to do is to write this, and that's, at least always try to write the setup just in case someone complains, right? And you want to find a solution that it is between this and this, but indeed that's what we are going to do. We are going to open Desmos here. Thank you. And then we are going to write that function, which was logarithm. You may remember. You can use the just this, and it will recognize that it's logarithm. So that's great. And then we had t squared. Should we use t or x? Later on, we will compute a derivative. I mean, honestly, you can use t or x, of course. But if you use x in Desmos, you automatically get a graph. And that might help you for some other questions too. So we are going to substitute all the t's by x. So it's going to be x squared, and then minus 4x was right, minus 4x, and then plus, of course, it's plotting, it's working for us while we do something. Not yet, guy, wait for us. Minus 0, but he cannot wait, right? So it's just computing everything. Okay, good for it. So if we go now between 1 and 2, what do we find? We find here a point that if we click, it shows 0. So it's 1.4261. And we need the 3 digits. So 142 and 56 is going to be 6. So let's bring back our notes here. So let's see, good notes, and we have it here, and then yes. So we have that was t1 point something, right? Let's try to find it again. 42.6, and there are no units. Remember, no units. Well, we didn't ask for it, so that's it. Now, find for the times that are before this instant when the particle is at rest, is the particle moving to the right or to the left? So if we look at the graph here, so that helps to have this graph here, you can see how it's all the time positive. So you can say that since v of t is positive for 0 less than t less than this tr, the time of rest, then the particle is moving to the right, because for us, in a standard mathematical convention, positive means to the right. Okay, so that's it, end of the story. Now let's continue. Maybe we can still use this. Find the acceleration. Yes. So let's do it first with Desmos. So it's just going to be v prime at 1.5, and that's it. So how do we do that? Well, we define here a function. They say that this is a function. Wait. So yes. So let's move here and say, hey, this is a function. So just go to f. A function is f of x. So just write f like editor, then x parentheses. It's very cool. It identifies everything. So here we have the function again, the same thing. Now the next thing that we want is f prime. So you go here and say f, and then you say, well, I need a prime. If we would have this like full screen, you would find the prime in your keyboard. But otherwise, you go to functions, you scroll down, a little bit down. Unfortunately, they could have put this at the very top because it's so much used. And then you say, well, okay, great, but I'm only interested at 1.5. And that was it, minus 1. Woohoo! That's it, no units, done. That's great. Now, if, as I said, if you want to see whether you would be able to compute this by yourself and also understand how things work in more detail, then you can use this derivative. So you have to compute this derivative, which is, you know, something that you should be able to do without any problem, right? And substitute here the 1.5, and then 3 minus 4 is minus 1, 1.5 squared is 2.25, minus 6 plus, so it's minus 1, and then minus 0.2, and this is minus 1 divided by 1.25, minus 0.2, and this is indeed 5 divided by 4, and this is 1 divided by 5, so this is minus 4/5 minus 1/5, so minus 1. Ooh, same thing. It took me longer than Desmos, but yep. we are able to do it. But also we would understand that there is a constant term and there is this part which is the derivative and so. Anyway, that's something that we don't need to think about, but it may be helpful in the future for you. Now, what about this? There's a question, whether it's increasing or decreasing. Yeah, that's a very common question, so let's devote to it a little bit of time. Let's add here a page, because I would like to show a table. So in order to answer whether a particle is increasing or decreasing the speed, right? Yeah, the speed of the particle is increasing or decreasing. That usually is very tricky, because if you think, oh, the acceleration is negative, then it's decreasing. Well, if the speed is negative and the acceleration is negative, then it's increasing. It's like I'm falling, -10, and then the acceleration of gravity is also -10, so I'm going to fall even faster, right? I mean, the longer it takes to hit the ground, the worse. So, well, that's obvious. So it's going to be negative, but in an absolute sense, it's greater and greater. So you can make a simple table, but also remember, same sign, increasing, different sign, decreasing. You can say that, same sign increases, different sign decreases. So what we have is the sign of the speed and the sign of the acceleration. The sign of the speed could be positive or negative. It could be 0, if it's 0 is at rest. The sign of the acceleration could be positive or negative. If it's 0, it means that at that moment the speed is not changing. So we wouldn't say if the particle is increasing or decreasing. They could have said, is the speed of the particle increasing, decreasing, or neither at time? So at that, if the acceleration is 0, then it's neither. It's not changing, right? But usually you will have the same question over and over. So you have this and this, right? And then we have 4 possibilities, which is that either they have the same sign or not. When they have the same sign, it's increasing. So if it's positive and positive, there's no doubt, right? 1 meter per second, and then the acceleration is 1 meter per second square, is increasing. But if it's -2 meters per second and the acceleration is -0.5 meters per second square, then the speed is increasing in the sense that it's becoming more negative, right? And then if they are different signs, then they are decreasing, okay? That's important when you, for instance, consider the case of a spring that has positive speed, negative speed, negative acceleration, and positive acceleration. So you have this table in a spring that is oscillating. You will have all these possibilities, even the zeros too, okay? Okay, cool. So in our case, where are we? Well, we know the acceleration is negative. So we are here. Let's pick up, I don't know, this column here, right? And then the other thing is, well, we need to know the sign of the speed. So how much is the speed at 1.5? Remember, this was the graph of the speed. So if we go to 1.5, be careful, 1.5, it's negative, right? It's here. You don't really need to write the value. Simply, you need to know where it's negative. So we are here. So therefore it's increasing, okay? Increasing. It's like falling and falling even faster. Okay, cool. So we have solved this. Now, what is the next one? The position. Oh yes, the position. So remember, the position is going to be, the final position is the initial position, is at 1. And then the integral of the derivative between these 2 points. So you can say this, because this could apply to any problem. Now, in our case, this is the speed, right? It has a proper symbol, which is the speed. But other than that, then we can go back to Desmos and evaluate this. Notice that there is no absolute value, because it's position. As we were saying, you can come back to the original position. It could be 0, but you've done some distance. That will be the next question. So let's go back here and see how we do that. So first of all, we want to, well, you could do it in many ways. We have f of x, so we could even do an integral. But I don't think we need that later on. Anyway, let's try to do it. Let's try to do it that way. Let's see if it works. So I'm going to say that I want to know how much is -3 plus the integral. You could go to functions, but it's cool that you can also just type integral, and whoop, it's recognized. And then you have 1, then go here up, 4, and then what do we want? The integral of that function that we had before, right? So f of x, and then dx. So you can go here and type dx. It's very cool. It recognizes. Yes, we got it. Now, how many digits? 3 digits after the digital point. So let's see, -2.80 and then 288. Well, that's going to be like a 3, right? So approximately, better we say approximately. And no units again. So that was it. Yep. And always set up Yeah, set up your calculation. So don't just say this, because then you're going to get half of the points off. You have to show the setup of your calculation, okay? And then finally, we have the distance. So the distance, even though we may go back to the same position, yes, that's when I went back to pick up my wallet, well, I walked 2 meters. So then it's just the absolute value. So what we have to do for the change of distance is the absolute value of the speed. So it's always going to be positive. There would be a way of breaking up when the speed is, changes sign. If it changes sign and this is this integral, and then I have to change the sign of this integral, and this is positive. That's very, very cool. You need to find the roots between 1 and 4. We could do that, 1 and 4. Oh, we have 2 roots. So we have a first integral, this integral here, that would be positive. Then we would do this integral with a minus sign in front, and then from 3 to 4 with a plus. But in these days that you can use Desmos, just go to the point. You can check some of the things. But if you do that, that's very cool too. You learn about the roots, which of these areas has more importance in the total distance, or where do you spend most of the time, right? But anyway, another little comment. We started at -3 and we ended up at -2.8. So a little bit less negative. So you can see how indeed from 1 to 4, the speed was mostly positive, but it was also negative, right? But it was mostly positive. So that's why at least you get a little bit more towards the positive. So that looks correct. But in order to answer this question, we go back here and let's change this. So first of all, we remove this, we don't need it. And then here we have the absolute value that you have it here in the functions, right here. This is very, very useful. And then you have to close it here indeed, okay? Then you have this amount, so 0.58 again, 3 digits is enough, so like this, and there are no units. Okay, and that's it. And always show your setup for what you did. Okay, this is great. We are like over A+, and this is awesome. And I'll see you in the next one, okay?